we're going to start with graph theory. And what are the parts of a graph? Just to remind you, we have dots and lines, right? What are the dots called? Vertices or nodes. And we have edges. So we have nodes and edges. Okay, so sometimes we have graphs that have nodes and edges, but they have one more thing. So here's an example graph. Say that these are cities that are connected by interstates. What is something else that you might want to know about these cities and the interstates that isn't really marked on here, besides the names of the cities? Right, distances. So we can actually label the edges with weights or distances or any other number that we might want, like prices. So numbers we can assign to the edges will be called weights. So I'm going to pick some random ones here. They're not so random because they're actually in the packet on page 14 if you want to look. And you don't feel like drawing this again. So this is called a weighted graph because every edge is given a weight. And we can use these for lots of things. So we can use it for distances if this is representing connections between cities. We can use it for the cost of using a connection. So this might be ways that these things can be connected through to the internet. And they might be, you might have to go to this place and this place to be connected to see or whatever. And that might be costs of those connections. Or it might actually be, you could also use it for a time delay or whatever. You can use it for anything. But it's very, very useful because then you can make choices of optimal connections based on those weights. So sometimes you might want to connect all of these nodes by the smallest weight for every connection that you have. So one kind of graph that we have is called a tree. And a tree is a graph that has no cycles. Is this graph that we have, is that a tree? No, it's not a tree. So a tree would be the smallest connected graph that does connect all of the vertices but has no cycles. And we can just start deleting edges to make something a tree, but in this case, since we have weights, we might want to delete the largest ones in order to make a minimum tree, a minimum weighted tree. So if we do that, that's called a minimum spanning tree. So a spanning tree is a tree that spans all the vertices, and a minimum spanning tree is one that has minimum weight on all of the edges. So the total weight of the tree is going to be at a minimum. So let's figure out what the minimum spanning tree for this is. There's two ways to do it. And one way is in your notes, and there's another way. So how would you make a minimum spanning tree for this graph? Do what?
You can remove AF.
Yeah, we could start removing the largest one first, right? So we could remove this one. Then what? We still have some cycles in there, right? So we can take out FE next, and then why didn't you take out AB?
Because then it's not a connected graph.
Because then it wouldn't be connected. That's very good. So we couldn't take out AB. Can we take out CE? Yeah, we can take that out because still D and E are connected, but now we know we can't take these out. The only thing we have left is this triangle in the middle, so we're going to have to take out one of those. So if we take out BF, this should leave us a tree. So let's check it out and make sure that we have a tree left. So the way you can do that is just by redrawing all the nodes and then drawing in the edges that you left. Then it's really easy to see if it's connected or not because you shouldn't have any dots out by themselves. So here we have a minimum spanning tree. So if we want to know the total weight of the minimum spanning tree, we add up these numbers, which is 44, 53, 68. So 68 is the weight of the minimum spanning tree for this graph. So can we delete any more edges? No.
Well, we can't, but we can.
We can't, because then it would be disconnected. So how many edges does a tree have in it? Do all trees have, for the same vertices, have the same number of edges?
Yeah, we have one less than the number of points, right?
Yes, the number of edges is one less than the number of vertices. And why is that?
Because to connect all of them, we'd only need one less than that many edges.
Right, we need to have one less than every edge in order to connect them all.
One edge between every single word or pair of vertices.
Right. So we need to have one less than the number of vertices, otherwise it's not connected. So if I have any less than that, it won't be connected. You can think of that like if I wanted to think how many edges will it take, I would think of putting them all in a line and how many edges would it take to connect them that way. And then that's n minus 1. If I have n vertices, I need n minus 1 in between all the pairs, consecutive pairs. And that's the sort of simplest way to think of a tree. Okay, and this algorithm that we just used is not the normal algorithm. The normal one is to start with the smallest edge and add it instead of deleting the largest, but both of them will work. Right? Should work, because I should come out with the same number of edges and come out with the same weight. Okay, so it doesn't matter which way you do it. If you start with the smallest one first and make sure you add it, so what we would have done is drawn these dots and then added the BC edge, then the CF edge, then the CD edge, then DE, and then BA. So that's called Kruskal's algorithm if you do that. So Kruskal's algorithm will find a minimum spanning tree. So MST stands for minimum spanning tree. So in this graph, I'm guaranteed to be able to get from one node to another because it's connected. And this is a graph of minimum weight. So it might not be that the cheapest way to get from F to A is actually to go on this graph, but overall, this is the cheapest way to connect them all. Okay, because actually here we have 31 plus 5 is 36 plus 8 is 44, which is actually cheaper than taking that 47 edge that we took out. But if that one was any smaller, if it had been 42, then it would have been cheaper to use that edge than to go on this MST path. So this doesn't represent the shortest path between any two vertices. It just represents the smallest weight tree that spans all of them. Okay, there's some other things with graphs that we want to look at, and one is called an adjacency matrix. So in lots of places we've looked at matrices one way to represent a graph is with an adjacency matrix. So let's make a graph. And if I want to represent who's next to who, basically, I can make a matrix. Without even doing this one, what can you say about what this matrix is going to look like?
It's reflexive.
Okay, someone mentioned that it's going to be reflexive. Is it going to be?
No.
It's going to be symmetric.
It's going to be symmetric because if A is next to B, then B is next to A. It's not reflexive because I don't have any loops. I would need to have a loop going from A to A, or a loop going from B to B. I'd have to have all of them in order for this to be reflexive. How about irreflexive? Is it irreflexive? It is because
No loops.
it is because I don't have any of those loops. So A is next to B. And is A next to C? No. It is next to D. It is not next to E. So I can fill these out based on, so I know this is symmetric, so actually I can go copy this row into this column. Because these are what's next to A. Now next to B I have A, C, D, and E, so everything is adjacent to B. Next to C I just have B. And next to D I have A, B, and E. And E, all I have left is to put a 0 there. So this is a symmetric and irreflexive relation represented by this graph. And it's not a directed graph, so if it doesn't have any arrows, we assume that the edge means that the relation goes both ways. So every graph can be thought of as a binary relation that's automatically symmetric. It's not necessarily automatically irreflexive because I could have loops. Why is this useful? Yes.
Because then you can easily put the graph in a two-dimensional array.
That's right. I could store this in a two-dimensional array in a program, and this has all the data about the graph that I need. Now, there's one thing that I didn't mention. What if I happen to have two connections between A and B? What should I do to my matrix? I should put a 2 in there to represent that I have two edges. So from A to B, I can actually put a 2 instead and a 2 right there, and then I know there are two of them. So that's the only thing I needed to do was make sure I just count up how many edges connect the two vertices that are adjacent. Okay, so this is one good way to store a matrix. So what's an alternative way to store a matrix? Store a graph. What's another way I could store a graph?
Coordinate location.
I guess we could do something like coordinate locations. I was thinking more in terms of, say, an array of the nodes, and then each one with a little linked list to all the neighbors. That's one way you could do it. Okay, so that might be useful for a different kind of program. So some programs might just want to know what's adjacent this way, and other ones, it might be better to make a linked list. Now, which ones, how do you know which one would be better? Depends on what you're going to use your program for, right? So what kind of program would a linked list be best?
One like airline flights where you might add cities later on. You want to go ahead and hard code the array.
That's right. It might be nice to have a linked list if I'm going to add cities, if my graph is really representing flights, connections between cities. If I want to add things, it's nice to have a linked list. Because then that way I don't have to actually go in 2 dimensions and add something. If I have a linked list with neighbors from each one, I just have to add to the city that I'm adding the flight. Another thing is if I don't have very many values in this matrix, like if there aren't that many edges, a linked list from each vertex might be the best way to go. Because then, say that this is like 1,000 by 1,000 and I only got 100 ones in there. If I only had 100 edges, I don't think I'd necessarily want to go by 1,000 by 1,000 matrix every time I wanted to find the neighbors. So you want to make choices when you create storage about what kind of storage you need based on how you're going to have to look through things. So when you have small things, it doesn't matter how you store it, except that linked lists are a little harder to code than arrays, right? So probably I'd do this, the first choice. But for larger things, you have to start thinking about, why do I need this data? And then you want to store it in a way that makes it easier to retrieve whenever you're going to do the most retrievals, right? Okay, good. So a linked list would also be useful if I need to get all of the neighbors for something, because that would be real quick to go through all of them. Okay, how many people have their handouts with them? Everybody, pretty much? Okay, I'll just put this one up here. All right, one next thing, which I don't want to talk too much about, but one concept in graph theory is called an isomorphism. And that's kind of an intimidating word, but I just want you to see these pictures right here. In your notes, it has a graph isomorphism is basically when you have a graph that's the same shape as another graph. So it's really the same graph except somebody rearranged the picture. So these top two, these are isomorphic. But you might have to make a mapping from some of the nodes to the other nodes. So in this case, if we take a look at these two, I can see that these two are isomorphic if I look at this little triangle, V5, V4, V3. They're the same in both pictures. And then if I think about taking these, picking up V1 and V2, and then stretching them down over the other triangle and making it bigger, then you can see that these two things are isomorphic. But without someone telling you that these two graphs are the same, you might not see it. So you might want, if you need to know that two graphs are the same, like someone's sending you a bunch of data, and you need to know whether you have the same data over and over again, you might check, two things and see if they're actually isomorphic. And the way to check is to see if the adjacency matrices are the same. If you interchange the rows in your matrix. Because you could have relabeled the vertices, right? So they might still be the same graph with relabeled vertices. So isomorphism means you have a graph of the same shape, like all the nodes will have the same degrees and stuff, but I might have to relabel them. And these two graphs on the bottom are also isomorphic. So you can see that by seeing that actually a line was drawn from V1 all the way to V7. See if you go around this curve right here, around the outside, you can see that that's the same. And then these other two are these crossing edges. Now, the reason why this is significant is because sometimes you need to make graphs planar. Because if you don't have them planar, they're kind of hard to read. Like you might think that there's a node in there. And there's lots of neat theorems about planar graphs also. So this one happens to be planar, but you can't tell in this picture. But if you draw it again in a different way, you can tell that it is planar. I can fit it in a plane without crossing any of the edges. That's what a planar graph is. So I just wanted to do a little brief introduction of that. I'm not going to make you do any isomorphisms because they're a pain.